to see what kinds of question you should expect in midterm exam. For example, what is the convergence test? Those kinds of questions. How many errors we have in FEA? Those kinds of questions. All right, that's in terms of conceptual question. Also, we have DSM, direct stiffness method, and that would be, oh, that one, sorry, this one should be MATLAB, I should Excel, come on. All right, now what's happening here is you will have question based on direct stiffness method that we are going to practice this week and next week. Is from chapter 4, and also you will have question related to simulation with SolidWorks simulation. Marking a scheme, this is what we have. We have conceptual question and DSM, this conceptual question, and also direct stiffness method using MATLAB. That total would be 25 marks. And using SolidWorks simulation to solve the problem for FEA, we have 15 marks. The total will be 40 marks. In terms of the software, all you need is SolidWorks and MATLAB. Make sure that both are available. Also, both softwares are available in Apps Anywhere. That is something that I'm going to talk about this one next Wednesday again. This is just a heads up what's going on in terms of midterm exam. As I said, early October, or sorry, end of October or early November, but the time it depends on the because we have 2 weeks we are losing 2 weeks in this course. We have Thanksgiving and there is another one in November. Then I have to work around that date and time. All right, let me just back here and see if you have any question about what I said in terms of midterm exam, the format, the content, the marking, and so on. Chris, it's not damn. DSM, yeah. It's a direct stiffness method, not direct simulation, direct stiffness method. This is what we covered, yeah, last time. I thought you were saying, what is this damn direct stiffness method? Are we going to have to solve problem on SolidWorks? Yes, as I said, we have 15 marks based on SolidWorks simulation, and we have 25 marks based on direct stiffness method, which is MATLAB, and also we have a conceptual question. Can we get more practice problem? You haven't had any lab so far. You want to have extra? I think it's good. The material that you have is good enough, and also you can later on you can see that you can use all the material that you have in a strength of material textbook, one-dimensional, axial, or torsion. You can use those and those examples and solve them with SolidWorks simulation. Because when you know the approach, doesn't matter how many problems you want to solve, the same approach you have to go through. Can we get more? Okay, that answer. We had an issue last time in lab where everyone was getting different stress values, like a range between 90 MPa. We shouldn't have 90 MPa range. When you say 90 MPa, the difference between the result, it's not acceptable. Something is not working properly. Just send me the file and I can look at that one. We shouldn't have 90 MPa different, no. Unless you go through what's happening in terms of the convergence test. Maybe the first try, which relatively a big size element, and then you're going to refine that one, and at the end it's a relatively small size, then definitely you have huge difference. There's no doubt about it. That's a convergence. But other than that, if you go with the same setup between two computers, you should have more or less same. It doesn't have to be exact number, but not 90 MPa. And lab instructor, okay, let's see. I'm not sure. I see what you mean, but I'm not sure, Nick, what was the problem? But you shouldn't have 90 MPa unless there is some bug or something in, I don't know, in your program, maybe you have to reinstall the software. You shouldn't have that range of difference unless there is something that I need to look at it, and I can't comment on something that I haven't seen in terms of the problem. But however, for midterm exam, just let you know that I'm just going to make sure that the problem is straightforward in terms of the simulation, and you shouldn't end up with a surprise negative way on the midterm exam in terms of type of question or simulation and those problems that you may have. I'm okay with that. I'm good at that because I'm teaching this course for years, and I know how to manage it to make sure that the students don't have any problem, especially now that it's online. Yeah. Any other question? All right, then let's get started. I'm going to record the session, and again, you have time. And as I said, don't worry about midterm right now. I wanted to give you a heads up what's happening in terms of the content-wise, marking the scheme, and type of question. But the exam won't be at least in the next three weeks. We are talking about end of October or early November, and we are going to talk about that one more next week. All right, let me just share the screen, and at the same time, I'm going to record the session.
This meeting is being recorded.
All right. I think we talked about this one. It's clear. As I said, next week we are going to look at this slide one more time in terms of midterm exam. Now, we covered the fundamentals of direct stiffness method last week, and we said in order to solve one-dimensional FEA based on DSM, all you need to do is you need to look at the element stiffness metrics, global stiffness metrics, and the equation governing the relationship between force and the displacement, which we had it like F equals KD. And we had an example to go through the direct stiffness metrics, and you're going to practice that example this week during the lab session. Next is we are going to practice and see how we can use SolidWorks simulation to deal with one-dimensional structural element. Well, just a reminder from Monday, when we say one-dimensional structural member, it means that the member is under either tension or compression in terms of loading, or if there is a torsion, what's happening is you have only torque applied to the member, which is you have twist. Then the theta would be, or the twist would be the degree of freedom. In terms of SolidWorks simulation, then now we are going to move to what is called multi-body environment. to create structural members. And this is something new for all of you, because we didn't have a multi-body environment so far in this course. And this is part of the material that we are covering in this course, and you're supposed to know it for midterm exam, final exam, and homework assignment. It's not complicated, but it's something that you have to practice a bit to get familiar with how to create dimensional, structural member or one-dimensional structural member. When we're talking about beam or truss, then we have to be careful about the definition of beam and truss. And when we say the definition of beam and truss, we are going to look at what we learned in our strength of material course, and also static. If you remember, the definition of beam is clear. We can assume any member and treat it as a beam as long as it is going to have a long or a slender shape comparing to the largest diameter in cross section. And that was the ratio. For example, in some book, they say something between 15 to 20. If the length of the member is 20 times that the biggest diameter in the cross section, then you can assume that one is a beam. I don't want to go that direction. That's the strength of material aspect of beam. And if that's the case, then you are going to, the beam theory is there. Then you can look at the sigma and normal stress and say normal stress sigma equals MC divided by I. You can look at the shear stress in beam and so on. Then the assumption is you can consider a member a beam, and then you can apply the beam theory. That is, as I mentioned, a strength of material aspect of beam. When it goes to SolidWorks and SolidWorks simulation, here's what's happening. It is you have three different approach to create the beam. The first one is you are going to use what is called a structural member approach. In this case, we are going to use weldments in SolidWorks in order to create the members. And then when we go to SolidWorks simulation is going to treat the weldment as a beam. And weldment, for example, if you have, look at here, if you have, for example, I-beam, if you create a part made of I-beam, and this is the structural member, this is the weldment in SolidWorks, and you're going to use a weldment tool in SolidWorks to create that. You're not going to apply extrude here. You're using weldments. Then what's going to happen when you go to FEA is going to treat that one as a beam. Automatically, the default element will be beam element. And for some cross section, they are not a standard. For example, this one is a standard, and we have L beam, I beam, say L bracket, C channel, and so on. Those standard cross sections, we have it in weldment. There are some beam that the profile, the cross section is not a standard, same as what I might draw here. In this case, you can create the customized weldment. You can create this one and save it in SolidWorks weldments library, and you can use it as you use for solid structural member approach. In this course, that is beyond the scope of this course. We are not going to look at this one, just for your information. And the third one, what I call non-structural member approach, meaning that what's happening here is you have solid, and you are going to create a solid model. You are not going to use weldment. You are going to use solid model, and then you are going to convert or treat the members in SolidWorks simulation as beam members. Then let me summarize what I said. What's happening here is, in order to create beam elements or treat a member as a beam in FEA, you have three options. If you're dealing with a standard cross-section, use Weldman. In SolidWorks simulation, is going to automatically consider that as a beam. If it's not a standard profile or cross-section, you can create, you can save, and you can use it later on beyond the scope of this course, this item. And the third option is you are going to create a solid model. For example, you are going to create a circle, apply extrude, and you have solid. Then you go to FEA, you have solid, you don't have Weldman, but you can treat it as a beam. Those are three approaches. When you do that, when you go to SolidWorks simulation, what's happening here is you are going to create parts. For example, you can go with, say, let's say with the third approach, which is a non-structural member approach. Then here you are going to create these three solids. And now there is one item here, which is merge result. Here's what's happening. If I want to create this part in SolidWorks, I can draw a circle, or I can draw a polygon here, and then I can apply extrude, then another one in this direction, extrude, and then another one in this direction, extrude. The default when you apply extrude in SolidWorks is you are going to create one solid body, and the reason is there is one option here, which is this merge result is checked by default. It means that if you apply extrude from here to here, then when you're going to look at, say, this is the first member, you're going to create the second member, which is this one. Now, when you create the sketch on this plane, and then you apply extrude, if that one is checked, it means that now you're merging these two parts together. If you uncheck this one, you will end up with multi-body environment, meaning that although you are in the part environment, but now you have body number one and you have body number two. I'm going to demonstrate this one in SolidWorks later on. But just keep in your mind that for non-structural member approach, you automatically are going to, if you uncheck this item, you are going to end up with what is called multi-body environment. And then you can, when you have multi-body environment, when you go to SolidWorks simulation, you can treat those bodies as a beam. Say you have 1, 2, 3 bodies. If you uncheck this one, you will end up with 3 bodies in SolidWorks. Then you're going to go to in FEA environment. All you need to do is select those bodies, right click and say treat them as a beam. And SolidWorks now is going to consider as a beam. When you create the beam, what's happening here is you will end up with the concept of joint. If look at this part, if you assume that we have three elements connected together and 3 beam elements, then when you go to SolidWorks, here what's happening is SolidWorks is going to assume that from here to here you have one beam, and then from here to here you have another beam, and the third one is from here to here we have the third beam. My point here is, if you do not have multi-body environment, meaning that if you create this solid model in SolidWorks environment and then go to FEA, all you see is one piece of material. If you use multi-body in SolidWorks environment and create a multi-body that I'm going to show you, then what's going to happen when you go to FEA and you're going to treat those as a beam, then SolidWorks is going to automatically create joints at those point of at the points that you have 2 different multi-body. Here you have body number 1, you have body number 2. Since you have multi-body environment, when you convert to the beam, then it's going to put a joint over there. And here, all you need to do is you're going to go to edit joint, and you're going to select all of them, and automatically SolidWorks is going to apply the joint. And this is clear in your text. You can look at the definition. In terms of fixturing, we have more or less we have the same concept that we had in solid, but here you have to apply the fixture to the joint, as you see. Then, for example, if you have, this is the tutorial 4.1 in your textbook. In this one, we're going to apply force to this joint and that joint, and the part, which is 3 pieces of beams connected to a solid joint, then or fixed joint. And then we are going to use a fixed fixture to connect this part to the rest of our structure. Then what's happening here is you can apply fixed geometry, but this time you need to apply the geometry, the fixture to the joint, because now you have beam. In terms of loading, more or less, as you see here, we have the same property manager. You are going to select the joint that you want to apply the force. You're going to select the plane or to define the direction, or can be an edge to define the direction. Select, make sure that you are setting the unit, proper unit, and then you are going to say what is the direction of the force. In terms of meshing, something interesting happening here, and you have to be careful about what you see in SolidWorks simulation is, if this is the part, if you treat them as a beam, when you apply mesh, it's going to show you something like this, which has nothing to do with what you had in the beginning. One more time. See, this is the part, and as you see, this is cylindrical shape. For example, here diameter is 50, here is 18, here is 35, and so on. But when you convert them to the beam, when you treat those multi-bodies as beams, then and apply mesh, this is what you see. SolidWorks is going to discretize the model, and what you see in the graphics area is this mesh. And as you see here, you don't see the big diameter, small diameter. The reason is, just pay attention, please pay attention here. The reason is SolidWorks simulation is going to apply beam elements to this beam. And SolidWorks is going to solve the problem based on beam theory. The reality is, SolidWorks is not going to discretize this part. SolidWorks is going to solve the problem based on beam theory, but is going to give you this opportunity to probe and measure the result based on the number of elements that you're going to create here. Then what you see here is not, then we do not have discretization error here, because what you see here is not really discretization. It's just the way that you can represent the result. You can apply even mesh control and say, you know what, I want to have 50 elements here, but that 50 elements means that you want to have 50 point of measurement along, say, from this point to that point. One more time. When you use FEA in SolidWorks simulation, SolidWorks simulation is going to use beam theory to solve the problem. It's not going to really discretize the beam, same as what we had in solid element. It's going to solve the problem based on the equation, but it's going to, when you say mesh it, it's going to represent the result and along the beam, and you can measure them. And you can even apply the element, say, mesh control. Mesh control here is, I want to have more points to measure, because SolidWorks is not going to solve the problem based on the discretization of the part. It's going to solve the problem based on beam theory. And when you finish, you end up with post-processing. And I'm going to show you in SolidWorks, post-processing means that, again, you have lots of parameters that you can measure, including reaction forces. See? Remember, when the beam was statically indeterminate, then you could not solve the problem in a strength of material. And we had one example 4-1, chapter 4, example 1, that you had two fixture at the both end, and you had one equation sigma f x equals 0, and you had two unknowns. And you can use direct stiffness method to solve the problem. Same happening here. You can, SolidWorks is going to solve and give you the reaction forces. Wonderful tool. Then whenever you have a steel structure, chassis, frame, and beam, then easily you can use SolidWorks simulation to calculate the reaction forces. And you can find more than that. This displacement is here, and also you have the moment, reaction moment, and also you can measure the rotation, theta. If there is a beam is deflected, then you can remember, based on beam theory in a strength of material, you had y representing the magnitude of deflection, and we had a slope, theta. And you want to measure y and theta when you apply load to the beam. Now you can measure those in SolidWorks as well. Now let's demonstrate what I said so far based on this example. I'm going to create this a CAD model from this one, and I'm going to apply boundary condition, do measurement, and demonstrate the material that I covered so far. All right, let me just share SolidWorks. In the meantime, please open your textbook and look at page 4-7, example 4.1. You can see the sketch of the problem. At the same time, I'm going to create a CAD model of that. Okay, let me share SolidWorks. One more time, please look at page 4-7 in your textbook, and you can see the problem. And in that problem, we have three pieces of material, which is, in the reality is we have one, but we have three elements. And now we want to use SolidWorks to solve the same problem that we solved with direct stiffness method on Monday. I'm going to create a new part environment. As you see, I'm not going to create assembly. I'm going to create part. Okay. Now, starting from point 1, or starting from left, please look at page 4-7 if you want to see what's going on here. I'm going to select the right plane and then draw a sketch. We have 25 millimeter. The first part is 25 millimeter. I'm going to apply extrude. It's 125. There you go. I'm going to accept that. Please pay attention to the next step. I'm going to select this face, we'll draw the sketch, and this time I have 18. Okay, now see what's happening here. If I go to extrude, see, the default is merge result. If I don't pay attention to that one, apply extrude, what's going to happen here is still I have one body. We do not have multi-body environment. And here what you see is, let me open that one. See, we have solid body 1. It means that we have only one solid body. We do not have multi-body environment. But if I uncheck that one, and the length is, I think, 90, and extrude, now if I apply that one, now see, we have two bodies, body number 1, body number 2, because we have multi-body environment. And that's a concept of body in SolidWorks. You can have two bodies creating one part. You can have one body creating one part. There are different applications. I don't want to go that direction in terms of SolidWorks, but it's a very interesting environment. As you see, at least for us in this course, we are using FEA. It's a very powerful. Now I'm going to select and draw the third one. I'm supposed to have 3 bodies here, yeah? Let's see if we have it. See, 1, 2, 3. Now let me save this. Okay, save the part in that folder. I'm going to go to simulation and see what's happening in simulation. I'm going to create a new static and delete that one as a static. Now, see, I'm in a SolidWorks simulation environment. And as you see here, we have 3 bodies. If you uncheck the merge result, here you see only one part. But what we have 3 solid bodies. Now, what I'm going to do here is I'm going to say I want to treat those selected bodies as beam. If I say that one, maybe it's wrong, maybe it's right. Can we assume those are beam? This is your knowledge. This is the strength of material. There are some assumption here that you are going to make, because if there is long enough comparing to the cross section, then you can say it's beam. But this is your decision, not SolidWorks simulation decision. I'm going to say, okay, you know what? I want to make these 3 beams, and let's see what happened here in terms of the symbol. Now, instead of solid, you have beam, and here in the graphics area, you have beam number 1, you have beam number 2, and you have beam number 3. You have 3 beams. And the interesting thing here is, since now we have beam, we have joint. Those are the joint. If you go here and say edit, this is what you see. See, SolidWorks is created automatically for joint. Joint number 1, joint number 2, 3, and 4. And as you see, if the joint is the middle joint, the color is some sort of, I don't know, it's red and pink, I don't know, cyan maybe. Let's call it red. We have red color for those joints in the middle, and we have green at the ends. Just differentiate them here in terms of where they are. And if what's happening, sometimes you create the model and you want to redefine the joint. All you need to do is invoke this tool, select the component of interest, and then say calculate is going to list the name. This is not the case here. Then I have 4 joints and I have 3 beam members. I'm going to accept. Now, what's happening here is I can say, in terms of fixture, I can come here and say apply fixed geometry. I want to apply fixed geometry here and there. Let me make the symbol a bit bigger. Okay, this is what we have, and let me change the appearance. Let's go to wireframe is the best. Let's go to wireframe. See, I just changed the appearance. Now, remember we said the definition of fixed geometry. Arrow means no translation, and disk means no rotation. Now, you do not have any rotation, any translation here. Same is here. And if you look at page 4-7, this is exactly what you have. Those are fixed geometry. I'm going to accept that. I need to apply force. I'm going to say I want to apply force. And I want to apply force to the joint because force applied to this joint and that joint. I'm going to select the joint and I'm going to select this one for the first one. And I want to say that force has to be perpendicular to right plane. All right. And the magnitude is, this is a perpendicular, see normal to plane. Those are direction 1, direction 2, and we have normal to the plane. For now, I'll talk about these two next week, but let's focus on this one for this week. And here you have 50,000, and let me just change the symbol. Pay attention to the direction of force. See, that is not supposed to have. We have to reverse the direction. I'm going to accept. Let me quickly apply the second one. All right. Next is I need to add material. It's 1020. Now I can go here. See what happened. If I go to mesh, I can apply mesh, but this is what you see. It seems that everything disappeared. But the reality is those are SolidWorks. If I run this simulation right now, SolidWorks is going to solve the problem based on beam theory, and you can probe the result for any of those points of interest. Or even you can apply mesh control. But mesh control doesn't mean that in beam case you have more precise result. It means that you have more point of measurement. Let me just run. There you go. Now its problem is solved, and see what we have here. I go to here. That's the stress result. And here you have some options. See, the default is upper bounded axial and bending. And you can measure the torsion, you can measure shear. We talk about those a little bit more in more detail next week when we talk about, next week, the week after when we talk about beam. Since we simplified the problem to one direction, all I want to measure is just the axial, yeah? Because if there is axial load, you should have only axial stress. And as you see, it's not a significant difference with what we had before. Also, we can come here and say, I want to define a stress plot. And we can create another one if you want. Chart option is more or less same as what you had before. Not a big difference. See? And setting is more or less same as what you had before in chapter 2 and 3. And in this case, I'm going to say I don't want to create another result. Another option that you have here is displacement. You can go here and say define displacement plot. And here you see you have lots of options. One of them is reaction force. I want to measure the reaction force. For example, Okay, sorry, let's go. And this is the reaction force. The graph is here. I can probe now. Same as the tool is same as what you had in chapter 2, yeah. And now if you zoom here, maybe I have to redo it again. I have to make sure that I'm selecting this joint. I'm going to say probe. Okay, it's not selecting. There you go. Maybe that's better. There you go. That's a reaction force. See, you have to make sure that you are selecting the joint. Yeah, it's gonna give you the result based on that joint. Then I have the reaction force. And other than that, I can go to animation and animate this simulation here. As we expect here, let me just make sure that the deform, yeah, the deform result is there. And this is what's going to happen. You do not have elongation here, and we expect that, yeah, because it's fixed. But you do have elongation in this area, because whatever you have here is change of the length, but the total length should be constant because we have fixed geometry here and fixed geometry there. All right, let me just stop sharing and stop recording.
The recording has stopped.
All right, now what I did, as you realize, I went through the SolidWorks simulation and what we have for one-dimensional beam element. What we have is in this week during the lab session, we are going to practice DSM and also SolidWorks simulation for one-dimensional beam element. Next week, we are going to look at the truss structure, which is two direction. We have 2 degrees of freedom. It's a little bit more complicated, and at the same time, we are going to look at both 2D and 3D truss. Any specific question? We have a couple of minutes, and I'm ready to answer your question if you have any. Okay, if it seems that there is no question, let's call it a day. And see you on, some of you on Thursday, rest of you on next Wednesday. And happy Thanksgiving, by the way.